Okay, welcome everyone to today's DDPS seminar. Before we go into actual, the fun part, like the actual presentations, let me go over some logistics. As usual, the talk is going to be recorded and will be available in YouTube channel, and also it's open to the external audiences, so no classified discussion. Please watch out for that. And please mute yourself during the talk. And if you have questions, you can unmute and ask questions. But if or you could leave your questions in the chat room. All right, so that's about it for the logistics, and let me introduce our speaker today. I'm honored to host the Youngjun Hong, who is an associate professor at Seoul National University, and he focuses his research on the mathematics of machine learning and its application in scientific computing. He earned his PhD in mathematics with a minor in scientific computing from Indiana University under the guidance of Professor Roger Hemam, where he developed a strong foundation in theoretical analysis and computational techniques. During his postdoc work at the University of Illinois at Chicago with Professor Jerry Bona and David Nichols, he conducted research on electromagnetic and water waves, further honing his problem-solving skills. He later initiated independent studies on the use of neural networks in scientific research, leading to a focused research program at San Diego State University, where he began investigating neural network approximation within scientific machine learning. Currently, his work is dedicated to developing theoretical frameworks that enhance the reliability and applicability of neural networks in addressing complex scientific and engineering challenges. Today, Professor Hong Youngjun is going to present us on his work on operator networks based on the numerical analysis. I'm sure he's going to give a fantastic talk. Before I pass the baton to him, let me ask.
Well, I'm sorry, I'm lost connection.
Yeah, no, I think Youngsu lost the connection.
Okay. So
I'm so sorry. Yes, I lost my connection. My computer just shut down on me all of a sudden. I'm sorry about that, but I was able to connect back pretty quickly using my cell phone technology. Hopefully the recording is still going on. Okay, so recording is still going on. Oh, okay, awesome. Okay, so I think I was about to ask a questions, right, Youngjun? So my question is, if you can, share your story, how you ended up with on this research field, like the scientific computing and the computational science, etc. If you can share some story, especially for the young, students, that would be very helpful.
thanks. First of all, thanks for a very nice introduction, and it's my honor to speak in the presenting the DDPS seminar. From the Youngsu's questions, so in fact, when I start my PhD, I have no idea about the scientific computing and of course machine learning, this kind of thing. Actually, I want to study some theoretical mathematics at the beginning, and I attend my former advisor's class, which is Navier-Stokes equations and some kind of the numerical schemes and theoretical numerical analysis, and then I dive into that kind of the new research, and it's fascinating. So I love it, and I just thought that, okay, this is the area I want to study right now, and then I dive into this kind of area, and then it's very, very interesting to me. So in fact, there is no special region to me. There are no kind of special moment to me, but I gradually like this kind of the scientific computing and machine learning field, and there are many good collaborators and friends in the laboratory, my advisor labs, and I can interact with many of the wonderful colleagues and the coworkers at the time. And yeah, I think that's the reason, because the subject is very interesting to me, and there are many, nice collaborators to work with me. So I think that's one of the reason. And the other reason is scientifically I want to study this kind of some real world application problem. That's another reason for me for the moment.
I guess you're, born to be a, work in the scientific machine learning. Well, thank you. Stage is yours.
Okay, thanks. So once again, thanks to Professor Dr. Choi and the DDPS seminar organizers. So it's my honor to speak here. So today I'm talking about the operator networks based on the numerical analysis. So I think everybody knows what's the scientific machine learning right now. So I don't need to speak of this kind of what's the scientific machine learning, what it is. But yeah, long story too short, it's like the machine learning plus scientific computing. So we are going to solve some scientific engineering or mathematical physics problems by using data-driven or sometimes some kind of the machine learning techniques. So it's kind of the new area, and it's multidisciplinary area. So it's very interesting to me for the moment. Okay. Although I'm talking about the AI today, I'm a mathematician. So before I dive into this kind of the machine learning fields, I'm studying this kind of the boundary layer and singular perturbation in fluids, ocean circulation problem, and sometimes some Navier-Stokes like equation. I studied this kind of the singular perturbation and boundary layer, and sometimes interior layer problems. And also I studied electromagnetic wave numerically by using some kind of spectral element methods and finite element methods, and I studied this kind of basically I solved the Maxwell equation by using some numerical methods, this periodic layered medium problem. So that's one of my subjects, and also I studied geophysical fluid dynamics. So this is famous the primitive equations, which is good for the numerical weather prediction, and I'm using the finite volume method and then solving some kind of this kind of the rain shadow effects by using this kind of excuse me, this kind of the primitive equations. But right now my interest is in the machine learning and scientific computing, in the combination of this in between them. So I want to make a bridge between scientific computing and machine learning and make a good development and good improvement for this kind of the new fields, new research fields. So okay, so right now with the scientific machine learning, we have two kind of the famous option, one for the physics informed option, and the other one is data driven options. So many people knows what's the physics informed neural networks and enriched methods. So they are not using some kind of the data driven methods, but they are successfully find solution for the given PD problems. And another field is data driven methods. So it's so-called a neural operator, and we have two famous neural operator. One is DeBonet, the other one is Fourier neural operator, and they are kind of the data driven. Sometimes they don't use data, but normally they're using the data driven methods, and then they can find the numerical solution with multiple instances. So there are two kind of the big two area to research fields like the physics informed and data driven. So let's talk about just a little bit more detail about the physics informed neural networks. So this is famous physics informed neural networks. So we have the spatial coordinates and temporal coordinates, TNX, and then we can predict the given solution. And how can we train this guy? We can train this guy by using the residual information. And so this is like the For instance, we are going to solve the Burgers equation, initial condition, and boundary condition. These are all the residual information or into this kind of the Ross function. And then they can using the auto-gradient and auto-differentiation by using the PyTorch or TensorFlow. And then they can find this kind of the derivative term, and then they can training this kind of the Burgers equation solution. So it's pretty much well known, and then it's very powerful because basically it's mesh free, and we don't need to know this kind of the data driven approach for that. So that's the physics informed neural networks, and the other one is operator learning. So one of the drawback for the physics informed neural networks, this is they can only predict single instances. So if they want to find another solution, they changing the forcing term, initial condition, they have to train once again. So to overcome this drawback, the researchers find this kind of operator learning, so they can handle the multiple instances, but they need some kind of the input-output paired data set for the training process. So basically, the operator networks, they can learn this kind of the mapping. So input is, for instance, input is like the initial condition, and they can predict, they can find mapping for this kind of the t is equal to 0.5, t is equal to 1, the given time, the solution data, a solution for the given PDEs. So they just find, they just basically learn the mapping from initial condition to the specific solution, initial condition to the specific solution. Or sometimes they give a forcing term and then find a solution. So they can do multiple instances. So they can change the initial condition, they can change the forcing term, then without further training, they can predict the numerical solution. So that's the operator learning, operator networks. And they can do the multiple instance. It's pretty much efficient in terms of the engineering perspective. So, and then this kind of approach is pretty much natural in the computer vision task, because computer vision, they have some kind of input image, they can predict the output image. So it's kind of the computer vision, it's kind of the mapping process. So they can do, for instance, we have this kind of the Poisson equation. So input is this kind of the forcing term M, output is the given solution. So input and output pair, and then they can have this kind of the neural networks. They can learn this kind of the mapping. So which is pretty much natural in the sense of the computer vision task. But we are going to use this kind of thing in the solving PDE problems. So one of the big branch is so-called the deep ONet. So deep ONet, they have two different network, branch and trunk networks. So in my understanding, this trunk networks is kind of the basis prediction, and branch network is kind of the coefficient prediction. So they can have some kind of the summation, coefficient and basis, and then they can predict the good approximation solution. That's my interpretation. And Fourier neural networks, FNO, so which is also pretty much famous, and so they have some kind of the stack of the batchified the data, and then they can inference the next time steps, this kind of solution set. So they are smartly using this kind of the convolution relation, and then they're using the inverse and forward Fourier transform. So input is this kind of the, for instance, initial condition and forcing term, and then using the encoder, and then they have a many Fourier layer in between, and output is decoder, and this is solution. And this Fourier layer consists of this kind of the MLP layer and plus Fourier and inverse Fourier transform. And then this R is kind of the reduction. So they can just get rid of the high frequency, and then they can just handle the low frequency term, and then they can adding it. This is one Fourier layer, and then they can process the many Fourier layer, and then they can find the nice numerical solution. And this kind of the process interpreted as this kind of the convolution operation. So I think the idea is very smart. So I like this kind of method. But I'm not going to talk about today about this kind of the known the operator networks. I'm going to talk about the new operator networks, which is based on the numerical analysis and numerical methods. So what is the pros and cons of the pins and operator networks? I think this is like the pretty much well-known part. So pins are very easy to implement, and it's basically mesh-free, so they can handle various domain and equation. And it's basically unsupervised learning. Some people, they say this is semi-supervised. Okay, it depends on their philosophy. And the negative part is they can predict only one single PD instance, and then maybe it's hard to impose the exact boundary condition. And operator network, they can predict multiple instances. So-called, they can solve the parametric PDEs, and they can use many, new trend of the computer vision architecture, like transformer and UNet, this kind of the architecture. And the one of the minus part is supervised learning. So they need pre-computed input-output data set by using the numerical PDE method. And sometimes they have some kind of generalization error, the high generalization error kind of thing. And let's just this is like one of the limitation or advantage for the scientific machine learning. So the limitation of the scientific machine learning is we don't have like some kind of concrete error analysis, and accuracy is not very high, and training time is too long. So it's kind of the limitation. But nevertheless, we need to study this kind of the scientific machine learning because the advantage is very, very, interesting, because they can overcome curse of dimensionality because it's sampling basis, and they can do the fast inference, and they can handle inverse problem very nicely, and potentially they can handle complex problem. And by using this kind of the machine learning, the expressive power, they can handle this kind of the complex problem. So these kind of advantages are very fascinating to me. So that's why I'm studying this kind of scientific machine learning right now. Okay, so this is very quick introduction. So now I'm going to talk about the operator networks with an aid of the numerics. So I think everybody in this room knows what's the numerical method for PDE. There are three famous the numerical PDE method. Of course, there are maybe 4 to 5 different methods, but I'm going to talk about the finite difference and finite element and spectral methods. Of course, we need to study also finite volume method, bounded element method, but I think if you want to study more, then you can just read the more textbook and more papers. But today I'm going to more or less focus on spectral method and finite element method. Basically, finite element spectral element method, they are rely on this kind of the weak formulation, and they need this kind of basis function. Finite element method basis function is local basis. Spectral element method, they are using the global basis function, which is orthogonal polynomial. So, and like maybe over 50 years, many of mathematicians and engineers and physicists studied finite element, spectral element, finite different methods, and there are many different branches, many different, the methodology for solving the given underlying governing PDE problems. So as I said, finite element method and finite spectral element method I'm going to talk about today. So finite element, which is good for the irregular and structured mesh, and then they need to use a local basis function. And the accuracy is, it depends on the order of the polynomial. If they're using the first order polynomial, the accuracy is not that high. But if they're using the high order polynomial, then the accuracy is they have a very high accuracy. And then computational cost is quite moderate. And then if you think about the spectral element method, they are using the global basis function, and like the Fourier-Legendre and Chebyshev polynomial, and they have a very high accuracy. Using the very small number of the polynomial, they can use the high accuracy numerical solution. But sometimes computational cost is very high, and they can handle just box-like domain kind of the problem. In general, of course, there are many different methods, but normally the global basis function is good for this kind of the box-like domain problem. So, motivated by the spectral method and finite element method, okay, let me start from the spectral method. I'm going to explain the operator networks based on this kind of spectral method. So this is the given elliptic problem. I said this is 2D, but not necessarily 2D, 1D, 2D, 3D, 4D, it doesn't matter. So this is like the elliptic problem. And then we can find reformulation from this kind of the problem, and this is given boundary condition. And then once we make this kind of reformulation, we can use the Galerkin method. We can find this kind of the solution approximation. And this Vx, Vk, this is basis function. So if you want to go for the Legendre polynomial, like this kind of a Legendre polynomial, then the basis function consists of this kind of the linear combination of 3 different Legendre polynomial. And then this AK, BK can be determined by the given boundary condition. For instance, if you have a Dirichlet boundary condition, AK is 0, BK negative 1. If you want to have a homogeneous Neumann boundary condition, then this is 0, and this is like this kind of the formulation. And of course, you can do the low-band boundary condition, and you can find AK and BK. It depends on the boundary condition. And well, this kind of the formulation, actually, I just am talking about the Legendre spectral method, but if you want to go for the Chebyshev or Fourier or the other Bessel function or Jacobi polynomial, then you can use another polynomial. Basically, the method is pretty much same, and the formulation is pretty much same. So what is my strategy? So normally when we think about the Galerkin method, so your solution UX, then you can interpret your solution by using this kind of the simple approximation. And this Vk is known polynomial like Legendre, Chebyshev, whatever. And this alpha k, which is unknowns, we are going to solve this alpha k by using the numerical method like Ax equal to b kind of the method. And so my idea is, okay, so this Vk, we all know this Vk is good polynomial because in numerics, we studied this kind of the basis function for 50 years, like the Legendre polynomial and Chebyshev polynomial, whatever this is, we can know this kind of the information of this Vk. So my strategy is that what if we can only predict this alpha k by using the neural networks, and then we can make this kind of summation. I call this one is reconstruction. Then we can find this kind of accurate numerical solution by using this approximation. So our input is given f, so I just naively make this kind of the simple random f. So given f, we can predict alpha k by using the neural networks. And once we predict alpha k, we can find this kind of by using this kind of the reconstruction, we can find this un, our numerical solution. That is simple idea. And how can we, and then the problem is, how can we build our loss function to train this kind of neural network from f to alpha k, given f to alpha k? So the idea is we can make use of the loss function, the weak form loss term. So for instance, very simple POI problem, like minus epsilon uxx minus ux equal to f, and then 0 boundary condition. And we know how can we build this kind of the weak formulation. And then this phi j are this kind of the test function. And then by integration by parts, we can, make this kind of term by using the integration by parts. Then this is left-hand side minus right-hand side. We want to make this is 0. If this is 0, then our un is good un. And then, this is the loss term. And then the question is, how can we pick up this kind of the phi j? Phi j is just test function. We have many options, many choices. But if we want to go for this kind of the Legendre spectral method, then this phi j are our Legendre basis function. Because this un can be interpreted as this kind of the alpha k and phi k. And this phi k is same phi j, like the same Legendre polynomial, that we can use Gauss-Legendre quadrature. The numerical integration is very high accuracy numerical integration. So we are going to use that kind of the numerical analysis technique. And well, this kind of derivative also exact because we know this form of the phi j Legendre polynomial. We know how to make a derivative for the given Legendre polynomial. And also this un, it consists of alpha k and phi k summation. We know what's the exact derivative for this part. So, we don't need to take them any kind of the numerical differentiation. So we can reduce the error once again. So these are the architecture for the Legendre-Galerkin neural networks. So our given external forcing term, f, and our neural networks, whatever the neural networks is, we can predict this coefficient alpha k. And once we predict this coefficient alpha k, we can reconstruct solution u hat. And then once we can reconstruct solution u hat, then we can make this kind of loss function. And then once we can make this loss function, then we can train these neural networks. And then you can, go in this process, then you can find accurate alpha k. as long as this process is, well set up, well defined. So that's the basic idea of the Legendre-Galerkin neural networks. Idea is very simple. And I tested this kind of 1D, 2D convection-diffusion equation, Dirichlet boundary condition, and then Helmholtz equation with the Neumann homogeneous Neumann boundary condition, and also this Burgers equation, so the zero boundary condition. And Burgers equation is nonlinear problem. So normally in numerics, we need to think about the iterative method, like Newton method or fixed point method. But our idea, we just predict alpha k. That's it. So we don't need to do the iteration process when we inference the solution, this solution to the Burgers equation. So that's another good part of this kind of the spectral coefficient learning, the operator network method. So convection-diffusion Helmholtz equation, we can find accurate solution. So this is a zero boundary condition case, convection-diffusion. And this is the Neumann boundary condition case of the Helmholtz equation. We can find quite accurate solution. In fact, this simulation is done maybe a few years ago. So right now we can do the 10 to negative 5 or 6 very high accuracy numerical solution. At the time, we didn't use the neural network architecture. So I just show the only solution, just it's quite accurate in that sense. But right now we have a more accurate solution by using the modernized neural networks. And so this is the Burgers equation with Dirichlet boundary condition. Also, nonlinear Burgers equation, we have a quite accurate solution. And also, I'm going to dive into this kind of the boundary layer problem. But boundary layer problem, we can also find very accurate solution. So I'm going to talk about this boundary layer later in detail. And also 2D problem, we can actually get the 2D problem. This is the predictive solution, and this is exact solution. We have relative L to error 10 to negative 4-ish, so which is quite accurate. So we can do also 2D cases. And once we've done this kind of the elliptic type, then we dive into the parabolic type of the problem. So time-dependent case. So time-dependent case, we have a u of t derivative. So the main question is, how can we handle the time derivative? So one of the very naive way, but which is very powerful way, we can just using the Euler method, implicit Euler or Lungi-Kutta kind of the numerical time derivative. So we can apply this kind of numerical time derivative. Then this is kind of the un plus 1 minus un over divided by delta t. Then they can become, again, one of the elliptic type of the problem. So we can iteratively inference this kind of the elliptic type of the neural networks. Then the other process is pretty much same. So we can, reduce our problem by using the time discretization by using the classical numerical method. And also we can do the Dirichlet, Neumann, and periodic many different boundary conditions. And the basic idea is pretty much same. The only difference is we have to handle this the time derivative parts by using the classical numerical the time discretization part. So that's basically our idea. So each time derivative part, time discretization, we have different neural networks, but we don't have like the 100 or 1,000 of the neural networks here. We have only 10 neural networks because one time set, these neural networks can predict like the 10th step of the time, and this guy also can predict 10th step of the time. So we can stack this kind of thing, and then make one big formulation. Then we can training everything, and then this is kind of all of this process is like the automation. So everything is automatic. So we can inference very quickly this kind of the whole the training the inference process. So for the time dependent problem, we have diffusion reaction equation, we have a nonlinear term, and viscous-Burgers and advection equation, and convection diffusion, and Gromov-Shibansky and Navier-Stokes equation in 2D. And we have various different boundary condition. So sometimes we have a zero boundary condition, sometimes we have periodic boundary condition, and sometimes we have a Neumann boundary condition. But every different boundary condition, it works very well because in fact we have this kind of the approximation alpha k plus vk. The basis function, in fact, the basis function has information of the boundary condition. So that's why our boundary error is 0. It's exact. So that's another good part of our method. Okay, so the Viscous-Burgers equation we can predict pretty much well. So we compare our method with two different the unsupervised neural networks, PINO, physics-informed neural operator, and Python, which is physics-informed deep net. So these are famous unsupervised neural networks. And then our SCLON, spectral coefficient learning operator networks. This is some abbreviation. Our method, this red one, which is the error is very low compared to the other methods. Oh, by the way, I didn't mention too much about this. As you know, our loss function, we didn't use any information of the input-output pair. So our method is not data-driven. So our method is unsupervised. So we don't need any kind of pre-computed data set. So that is another, the important part for our method. So that's why I compare our method with PINO and Python together. And the relative error is much lower than the other two methods. And diffusion reaction, advection, we compare to the Python and the other methods, and our method is like the low accuracy. So accuracy is very low. So the method is working very well. And in this case, advection equation, we don't have any kind of reference the method. So we only show the numerical the prediction. So exact and Skolun, our method, is quite accurate. So error is like 10 to negative 3. So time-dependent problem is also working quite well. And we move into the quite complicated problem to the Gromov-Toshimansky and to the Navier-Stokes. Of course, our method, well, it's not super great, but it's like the 10 to negative 2-ish error, like the 2% error, but it's working. So that's another, the 2D example. And so that's like the error comparison table. So our method, 1D advection, 2D Gromov-Toshimansky, we have 1% error. And the other method we compare with this one with Python, and then well, the performance is better than Python physics-informed DeepNet, and this equation, our error is better than physics-informed neural net operator, because our relative error to error is more or less 2% error. So that's kind of the numerical accuracy for the method. So again, our method is like unsupervised neural networks, so we didn't compare our method with the FNO and DeepNet directly. So after doing this process, as I mentioned, this is basically based on the spectral element method. But spectral element method, which is not good for the complex geometry, like the polygonal shape order geometry. So I want to do some kind of the complicated geometry, like this, circular or circle, the hole with the square and polygon shape, sometimes dolphin. So this example came from the Phoenix. So can we handle this kind of a complex geometry with our method? The answer is yes. The only difference is we can change our basis from the Legendre polynomial to the finite element polynomial, like P1, P2 polynomial basis. Then we can do it. So the architecture is pretty much same. The difference is we can replace our polynomial from Legendre to the P1 or P2, sometimes P3, P4. Then we can enjoy this kind of the complex geometry by using the domain triangulation. So the idea is pretty much the same. So we have this kind of the easy toy problem, like the reaction diffusion equation. Then we can think about the weak formulation. So this is the left-hand side and this is right-hand side. Then we can give our loss function by using the left-hand side minus right-hand side, the residual form. And then we can train once again by using this residual form. Then that's it. So that's the finite element operator networks. So again, I showed our architecture. So we have the given forcing term, input forcing term, and then we can predict this kind of coefficient by using the neural networks, and then this is P1, P2 element basis, whatever, P1, P2, each our choice. If you go to the P2 element, then you go for the P2 element, then you can make this kind of solution prediction, and then make a loss form, and then train these neural networks. And then going again, this kind of the process, like 1,000 epochs, then we can get the accurate numerical solution by using the operator networks. Again, this is unsupervised neural networks, so we don't need any the pre-computed data set, and this and the inference is we can do the multiple instances. So given input, forcing term, sometimes initial condition, sometimes boundary condition, which are input, then they can predict without further training, predict the numerical solution by using these kinds of neural networks. So, for instance, we tested this one is I think that is the Poisson equation or convection-diffusion, one of the equation. This is a linear equation, and then the domain is kind of the square with hole, polygonal shape of the domain, and then our input is given f function, forcing function like this, and this forcing function like this, and then I'm sorry, they just predict the numerical solution very well. This is ground truth, and this is ours, and that is DBONet with only 30 the data sets, input output pair. So of course, DBONet with 3,000 data set, they can do better, but ours are the unsupervised, so we just test with a very small data set. If we have 0 data set, so I think that's kind of a fair comparison. And well, ours are better, and also polygonal shape. This is ground truth, and this is ours, and this is DBONet with 30 data sets. So ours are also quite accurate. And this is another the interpretation. So ground truth, this is our input, and ground truth, and this is ours, which is good. And this is DBONet with 30 data set, which is a little bit, a little bit difference between here and there. And this is physics informed DBONet. So, and then this is another case of the physics informed DBONet. They cannot capture the solution very well, but ours are keep capturing very well. Look at this kind of the ground truth, and ours are finite element operator networks, so ours are better. And we tested many different domain. Domain 1, circle. Domain 2, square with the hole. Domain 3, polygonal shape. And different boundary condition, homogeneous Strickland, homogeneous Neumann, with this kind of equation. And also equation 1 and 2, which is general second order linear equation. Equation 2 is Burgers equation, which is nonlinear. And then we tested it. Basically, everything is like the percentage error. Like our errors are without the training data set. Ours are like the 1% and 0.5%, 0.1%, 0.3%, quite accurate, error prediction. So compared to the physics informed DBONet and compared to the DBONet. So of course we have a DBONet with 3,000 supervised data set. Sometimes it's good, sometimes it's bad because we have a very complex geometry, but ours are consistently have a good prediction. And the variable coefficient, so we have an input is a coefficient of the given PDE. For instance, we have Cx is coefficient in front of the convective term for the convection diffusion equation, then they can still predict a nice numerical solution. And also input as an initial condition, they can predict nice numerical solution. And we can do the little more complicated problem like the Stokes equation. In that case, we're using the Taylor-Hood, the P2P1, the finite element method. They can predict quite well. And also, we give an input the boundary condition like this and this part of the boundary condition. Then they can also, boundary condition as an input, they can predict very well. So these are the comparison table. So we compared our method with the POD DBONet, which is upgrade version of the DBONet. So coefficient, DBONet with 1,000 data, this is a little better, but basically ours are 0 data set, so ours are concretely fine. So, and then we make this kind of the error analysis. So like this is what we do in the numerics. So number of elements increasing, how look like the relative error, it's decreasing. And number of elements decreasing and the error also decreasing. But this is a little dent, so I'm going to talk about this one quickly later. So this is P1 and this is P2. This is 1D and this is 2D. And the red one is P1, blue one is P2 element method. So okay, I have only 5 or 10 minutes. So our method is also good for this kind of singular perturbation problem. So I think many of you already knew what's the singular perturbation problem. They can produce boundary layer or interior layer problem. So like this kind of the problem, as epsilon decreasing and decreasing, then they can produce very sharp transition near the boundary or near the interior. So it's really hard to capture by using the classical numerical method. Of course, they can use some adaptive mesh refinement. They can do better. But classical numerical method, it's really hard to capture. And also in machine learning, which is very hard to capture because they are related to the spectral bias. So spectral bias, they can learn the high frequency later. So it's this kind of the sharp transition, they can interpret it as a high frequency. So they can learn this kind of the high frequency very, very slowly. Or sometimes they cannot learn this kind of the high frequency. So they are closely related to this kind of the spectral bias. So singular perturbation problem quite important when we handle scientific machine learning problem. So how can we handle this kind of scientific the singular perturbation problem by using our method? So we go back to the singular perturbation analysis in PDE, and then we are going to use this kind of PDE idea into our neural networks. That's our idea. So okay, I don't have enough time, so I will skip this kind of analysis part quickly. So think about this kind of simple convection-diffusion equation and zero boundary condition problem. And from here, we can make asymptotic analysis. So asymptotic analysis means that we can capture only for the sharp transition behavior nearby the boundaries. So this is like our asymptotic equation. So we call this one is boundary layer solution. So when we solve this boundary layer solution, then we can capture this kind of sharp transition profile, whatever this is 1D problem, 2D problem. And for this kind of the convection diffusion type of the equation, so boundary layer profile is e to the minus x over epsilon. That is called the so-called corrector function. And in theoretical PDE, by using this corrector function, they can solve this kind of vanishing viscosity limit problem theoretically. But in our method, we are going to capture only this corrector basis, the corrector part, and then make it this one as our another enriched basis function. So this is like the P1, our finite element classical basis. And then we can add this corrector function into our basis function. And then we know this corrector function by using the singular perturbation analysis. And then this is called enriched basis method. So we can enrich our finite element basis by using this corrector function. Then this is the finite element space. And then we can do the Galerkin process by using this new finite element basis. Then we can capture the sharp transition. So this is an epsilon equal to 1 case. So they have no boundary layer for this equation. So they can do very well by using the finite element neural networks. And this is epsilon 10 to negative 5. They cannot capture this kind of sharp transition because they have a boundary layer, epsilon 10 to negative 5. But we add one more basis, which is no specific further cost, one more basis function, and then they can capture this kind of sharp transition very well. This blue one is exact solution. This red one is predicted solution by using the finite element neural operator, the FAONet. So adding this basis function, we can capture this kind of sharp transition. So we can handle singular perturbation problem very well. And time-dependent problem, I will show you this kind of time-dependent problem by using this video. So this is like the nu is 10 to the negative 5-ish, and our U0 initial condition, I will show you the initial condition. Oops. Initial condition is very smooth initial condition. This nu is small, then they can develop this boundary layer very quickly. But this blue one is the exact solution, and red dot is our predictive solution by using the finite element operator networks by using the new basis function. Then they can capture this sharp transition very well. So we can capture this kind of the boundary layer phenomena quite well. And the interior layer case, this is the FNO and COM FNO is like the triple AI paper recently published 2024. They used some kind of the similar idea by using the the FNO method, and they have a 900 training data set. But our method, FAONet, the finite element operator network, without no data, we have a 10 to the negative 5 accuracy for this kind of the interlayer problem. But the other method, they are good, 10 to the negative 3, but ours are a little better. But we have no training data. They have a training data. So that's the difference. So this is inter-layer cases. And then we can do the many different cases like the 2D and circular and elliptical and this kind of the polygonal shape. We can, have a further extension. And in fact, I didn't do this polygonal shape. This is another example, but I'm pretty sure we can do this kind of the polygonal shape by using the FAONet with special basis function. So 3 minutes, I have 2 minutes. I have so let me just talk about quickly the convergence analysis. So our approach actually based on the numerical PDE method. So we know. So we tried this kind of the rate of convergence kind of the analysis. So number of elements, this is relative error to error. So in FEM, we know that P1, P2 elements, we have the rate of convergence -2, rate of convergence -3. So theoretically we can enjoy this kind of the nice convergence for the P1, P2, the blue dotted one. But by using the finite element operator networks, we increasing the number of elements, then error going down, and then suddenly they are going up. Also, error is going down, and then suddenly the error is going up. So I thought that at the beginning, oh, maybe this is problem for the neural networks optimization. So maybe we can make use of the larger neural networks, then we can enjoy the better convergence rate. That's the first thought. But actually it's not. We changed our neural networks, changed the optimizer, then this kind of the phenomena keep, appearing in our analysis. So why this happening? What are these hiccups? So we dive into the convergence analysis. So our method is based on the numerical PDE. So we can do the convergence analysis by using the classical numerical analysis. So it's like the Thias lemma, Bramble-Himbert, and convergence theorem, which is in the FEM, and spectral element method. We know this kind of the error analysis. So we can make use of this kind of similar error analysis for the scientific machine learning. So I'm not going to dive into approximation, generalization, optimization. Let me skip those parts. So in fact, we make the error estimate for our finite element neural networks. Then we have this kind of the error bound. So that means what is kappa A? Kappa A like the condition number of the weak form matrix. So that means this condition number actually bothers our convergence. So we have like the high condition number, then our numerical error, relative error to error going down. So number of elements increasing, we know condition number is larger. So that's why they have this kind of the hiccups like this and this kind of hiccups. And this red one is like the theoretical error bound by using this kind of the upper bound. So we can make use of this upper bound and then we can just sketch it. So it's pretty much same. So that is theoretically we can prove it. So how can we handle this kind of the hiccups? Of course, we use the more number of the elements, more number of the neurons, then we can actually relax this kind of the hiccups. And another idea, so take M large, that's one idea. Another idea is we can use preconditioning. So once we can use preconditioning, we can just handle this kind of the high condition number. Then, with the preconditioning, we can have a better numerical errors without the preconditioning part. So that's one of the idea. So of course, this is just upper bound, and we didn't take into account the optimization error. The optimization error, this is different animal, so we have to handle more carefully. So that's kind of the ongoing research. So we are going to develop more and more this kind of the analysis part by using the neural networks. So okay, let me skip this part. So I also interested in this kind of the foundation model for solving PDE, but I'm not going to talk about this today. So let me introduce my collaborator, Professor Sung Chang-go and Jae-young Lee, and Nam-jun Kim. And these are my postdocs, Juno Choi and Jin-si Lee. They can help me to this kind of simulation and analysis all together. So we have a good team. So we keep working on this direction. And of course, this is not the best way to handle the PDE problem by using the scientific machine learning. So, but we can study more and more, and then we just feel that there are many more interesting parts of this kind of scientific machine learning for the moment. So that's the references. So thanks for the attention. Thank you.
Thank you. Thank you so much for the wonderful talk. Let's have a Q&A sessions. If you have questions, let me see the chat room. I don't see any question there. So if you have questions, please unmute yourself and ask questions. While you're thinking about the question, I guess I can ask some questions. So your method is unsupervised method. You don't need a data. So what about the computational cost? Like is it faster than the traditional way of solving, like using the finite element method or finite volume method, or is it slower, just like the pins, physics informed neural net?
Okay, so frankly, for the training, it takes longer time than FEM and FVM, of course. But by doing inference, we have much faster, because inference is just one neural network's just input and output process. So if you wanna predict like 5,000 numerical solution very quickly, then I would recommend our method is better. But if you wanna find 10 to the negative 12 numerical solution, then maybe you have to go for the spectral method or discontinuous Galerkin method. That's better.
Okay. So when you say training is slower, but once it is trained, you can inference. But when you do the inference, can you like inference on many different cases which you haven't trained on?
Yes.
Okay, so that details I think I have to
Yes.
capture.
Yeah. So like if you have a different forcing term, different initial condition, then they can predict very fastly, like the microseconds. They can predict many things. But
Awesome.
yeah. And I didn't specifically mention the foundation model things, but my dream is like to make a foundation model, like to make a different equation, different geometry, and then predict everything at once. But
Once
that's kind of,
it is trained, like
yeah,
once training is done and
yes,
multitasking,
yes,
multi-problem.
yeah, multi-physics, yes. But that's my dream. So it's quite far-fetched right now, but it's my first step.
Oh, awesome. Okay, I have another questions. One of the things for the singularity, the problems, in order to capture that sharp feature, you have to add like auxiliary basis functions. What kind of basis functions did you add?
So okay, that's very good question. Thank you, because I didn't have enough time, so I didn't specifically introduce what's the character basis. So in classical numerics, I studied the enriched basis finite element spectral element method, sometimes finite volume method. So I don't want to use adaptive mesh refinement because that's quite expensive. But I want to solve this kind of the boundary layer interior problem. So in that case, we can add one more basis, like the enriched basis, and they are basically boundary layer interior solution by using the asymptotic analysis.
Yeah.
So you can make asymptotic analysis for the given PDE. You can predict you can actually calculate what is the boundary layer solution, like the inner solution, so inside the boundary layer. And then whatever this is 2D or 3D, the solution profile could be 1D profile. Because if you have a very nice boundary layer. So of course, if your geometry is very much ugly, then maybe your character, the basis function is also ugly. But maybe if you have some nice kind of the domain shape, then you can find this kind of the character function. Then you can add this character function to the finite element basis. That is called the enriched finite element method. So I just make use of this new basis function into our the finite element operator networks. So
Okay.
it's basically PDE kind of the oriented idea.
Okay, awesome. Okay, so there, Liang Yang, do you have questions?
Yes, yes, please. Can you use the idea to other like finite difference, finite volumes, and meshless or boundary element, those kind of classical method?
Yeah, that's very a good question. I'm actually thinking that how can we make use of this idea into the finite volume method? But one thing bothers is that I have to compute flux, and it's like so it's not very easy to think about it. How can we just predict fluxes, so, and then for the different geometries? So it's not very straightforward. But I'm also thinking about how can we apply this idea to the finite volume method, and you know. I'm kind of big fan of the finite volume method, so because they have a conservative structure. So I love that, but yeah, I'm still thinking about it.
Yeah, I
Awesome.
think that's a great idea because combine the class computing method with the AI, the new methods. So those all and new combined together, I think, as you demonstrated in your talk, is excellent, wonderful. Congratulations.
Thank you. Thank you so much.
Thank you
All
very
right.
much.
Okay, we have another question from Kevin. He's asking, does the neural network output all coefficient values of the basis functions, or are there multiple neural networks each outputting one coefficient value?
Oh, it's like the one neural network's outputs to all coefficient values of the basis. So your output could be vector of the coefficients.
Okay, and the dimension of the output is like number of coefficients you have in
Yes, exactly. Yeah.
Okay, sounds good. Is there any other questions? If not, let's thank our speaker, Youngjun, for the nice talk. And hopefully, after this presentations, a lot of people is going to reach out to you and then, ask questions and also, establish a future collaborations.
Thank you so much. Yeah.
Okay, awesome. Well, with that, let's end our DDPS seminar today. Let me stop the record button.